important drawback and thing we will talk about is earthquake resistance and wind resistance. Buildings are not considered to withstand those sharp horizontal shakes, and that's why after 10-20 seconds of earthquake, many thousands of buildings can be ruined to the ground. So there is basically very easy construction method with putting absorbers beneath the house, but it's easy in theory. Practically, it's very hard to create something underneath your house that will absorb, in case of earthquake, those fast frictions, but it will help to protect house. I would like to show you some testing systems to understand how buildings and wooden buildings and mass timber buildings will perform in earthquake conditions. This is the biggest shake table in the world. It is located in California.
I'd always thought these skyscrapers would be the hardest hit in a big quake, but in fact, the taller the building, the more flexible it is. Skyscrapers can sway without falling over. What we need to worry about are thousands of buildings that went up before the 1970s. They're called soft-story buildings because their ground floor is an open space, usually a garage, with large doorways. In an earthquake, that structurally soft story can't support the motion of the upper floors, and it collapses. A 5-university team built a replica of a soft-story building from the 1920s. It's built on the largest outdoor shake table in the world at the University of California, San Diego. Powered by massive hydraulic pistons, this 172-ton brute can simulate the most devastating earthquakes ever recorded.
This is the first time a building this size that represents a true soft-story building has been tested.
His team will test 4 engineering solutions that performed well in computer models. The first retrofit involves panels of a new building material called cross-laminated timber, or CLT. CLT is made of lumber stacked at right angles and glued together, which makes for panels that are very strong and stiff. 2 sets of panels are placed on the garage floor and anchored to the ceiling. During an earthquake, they should rock in place and help absorb energy from the motion of the upper stories. But the CLT panels aren't bearing the burden alone. They're attached to steel rods that run straight down into the foundation.
The steel rods, that they have to transfer forces from the cross-laminated timber while it rocks, and this will dissipate the energy from the earthquake.
This will be a simulation of the 1989 earthquake that took 63 lives and destroyed countless structures. Can just a few wooden panels really prevent collapse? The original earthquake lasted about 15 seconds. That may not sound like a long time, but if you happen to be inside a building that's about to collapse, it must feel like an eternity. Cameras reveal the CLT panels rocking in place.
Isn't that interesting? So that one, this one yielded.
It's clear that the panels saved the day. But the rocking motion put so much stress on the steel rods that they actually stretched.
This is reconstruction of Chi earthquake that took place in Taiwan in 1991. Its magnitude was 7.8 and it killed more than 2,000 people. There were many buildings destroyed, the same from wood, concrete and metal, but this tall wood project was constructed recently and they proved that this project can hold earthquake of such magnitude. This test of 10-story building is remarkable in many aspects. It was the first time 10-story building was built and tested on a shake table. For the second, they used earthquake-safe design by using CLT plates that are called the rocking walls. And as you can imagine, the third point is that it's built from ecologically safe material, timber. An engineer, Joel Conte, told that this building was designed to rock with the shakes of the ground. As he told, the bottoms of building walls are rising up about an inch when this building rocks, and they are secured by flexible steel cables. Daniel Cheney is an engineering manager in that project. He told that timber constructions take carbon out of the air and puts it into our infrastructure. So it means that buildings that are made from wood, actually it's a place where we can store carbon, and it's good for environment, it's good for industry, and it's good for people. In case of those absorbers, there are many different ways to make them, and they can be very different, but the main way they are used is to compensate those horizontal shakes and make them not so rough. Let's take a look how this system works in real life. At the moment, Chile has one of the best shock absorbing systems against earthquakes in the world, and now we are looking at tallest building in Santiago. This system decouples the building from the base structure using those rubber absorbers. It means that ground can move in certain way while the structure moves a lot less. These isolation units works like shock absorbers on the car. When hit, they distort and reduce the effect of impact. Architect of this building told that purpose of anti-earthquake norms isn't to stop building from being destroyed, but prevent building from collapsing on people inside. Our next theme is wind resistance. Of course, we are nowhere near building wooden structures that would compete with highest concrete and steel structures like Burj Khalifa. It's more than 800 meters. Of course, we are constructing wooden buildings up to 100 meters, but we are not planning in the nearest future to go higher. But it's not even necessary. Very important is to use wood as recyclable, biodegradable and friendly to the planet material in many not so high structures. But it will change the way we are working and it will be more friendly to our planet. Of course, there are some tests going on, but in any case we can say that by placing steel columns and beams in the skyscraper's core, engineers create a stiff backbone that can resist wind forces. This inner core is used as an elevator shaft and staircase. So, in any case, this backbone will be made from reinforced concrete and metal elements. And in the right side, you can see their dome roofs. Dome roofs are considered to withstand higher wind forces than square buildings. The same you can compare it with tents that are in form of dome. They are more resistant in case of wind than square tents or other forms. Let's talk about the main elements of mass timber. We were talking about cross-laminated timber. Those materials are used for floors, walls, roofs, and planar elements. They are glued together with waterproof glue. The first one is glue-laminated columns or beams. Basically, those elements are made by taking pieces of wood and laminating them together. They can be straight or curved or custom shaped, and they can be used both in interior or exterior. By the way, you could see such structures in shopping centers when above your head there is glue-laminated wooden beams that are bent. This structure can withstand bigger pressure from upside down. The other elements are structural composites. LVL, which is laminated veneer, or PSL, parallel strand. It means that there can be different types of materials. There can be wooden materials such as OSB and other materials that are glued together, they can be used for beams and columns, but just straight ones. You can't make bent beam out of this one. And I would like to explain one more time about cross-laminated timber. As you can see, wood can split along the grain. So when you glue them together in perpendicular directions, one side won't let other side to expand, to change dimensions and to split. It will be very stable material. And here you can see all those elements together. In the first picture you can see glulam. Here you can see CLT plane that is used for floor and ceiling. And there is a close look to those CLT planes. And here you can see all those three elements. Glulam column, glulam beam, here and here and here, CLT floor and CLT ceiling. And how some of those connections have to be taken together through steel elements, here and here. So with some simple sentences, let's answer to the question why those pieces of wood has to be bounded together. The first one is that cross-sectional shape matters, as well as wood is lighter than any other material. So wood is 2/3 of weight of the steel, and it is 6 times lighter than concrete. So we can conclude that wood is light, it is strong, and it is good at bending. And here you can see one interesting project that is made by architect Shigeru Ban, and this is an office building built in Zurich in 2013. It is constructed from like a gigantic elements of glulam that looks like kids' toy set. But in that building we can see what is possible to do with glulam in terms of size. And if from glulam we can make columns or beams, then from CLT panels we can make floors and ceilings. It's the same. CLT panels are very stable, the same as plywood. And as you understand, plywood works because you take out the idea that wood can split parallel to the grain. You can take 2 layers, you layer them in 90 degrees, and if it starts to split along the grain, then it runs perpendicular to the other, therefore it doesn't split at all. The same CLT works. Finished CLT panels are typically from 70 centimeters to 3.5 meters wide, with length up to 22 meters, so quite big panels. Thickness of those panels can be up to 50 centimeters. There can be bigger pieces of those CLT panels. They can be up to 6 meters wide and with length up to 36 meters. Those dimensions are possible but uncommon because you have to have bigger thickness and it will require a lot more material. We can say that there are more than just cross-laminated timber. You can put those wooden pieces together using nails, and then it is NLT, which is nail laminated timber, or DLT, which is dowel laminated timber. In that case, you can see how it looks in real life. Those dowels gives additional strength to the panel. Wood is energy efficient. It is easy to heat room made of wood, and it is easy to cool that room. And because those elements are manufactured in a controlled environment, there are a lot less waste. And of course, there's less energy spent in construction and deliveries and assembling of those wooden structures. The thickness of CLT sheets depends on the size of the area to be covered without columns. As we can understand, all reinforced concrete panels that are used as a flooring elements in buildings are 22 centimeters thick, and above those constructions you can put any kind of floor covering, and altogether this panel with floor covering will be, let's say, 30 centimeters thick. It's a standard. But when we are talking about CLT panels, there can be different thicknesses. So if you have small room to be covered with this CLT panel, you might not need to use 22 centimeters thick panel. You might use, let's say, 12 centimeters thick. Or if you have a big auditorium that has to be covered with CLT and there is no column inside this room to hold it from downside, you may have to use 25 centimeters thick CLT panel. There is a floor load chart that you can use when you have to calculate the thickness of this